Here we have 1 kilogram of air with the pressure and temperature given at the initial conditions, and 3 kilograms of carbon dioxide also with the pressure and temperature given at the initial conditions. And they're on the opposite side of a rigid, well-insulated container. So here's a little partition that can move back and forth, but this box here is rigid and well-insulated. The partition here, of course, is free to move, as I just mentioned, allows conduction from one gas to the other without energy storage in the partition itself. And we're asked to find the final equilibrium temperature. Now the temperature will be the same at the final state between the carbon dioxide and the air because the partition is conductive. And then the final pressure, and the pressures should be balanced because if the pressure over here was higher or lower than the pressure here, then the piston would move to the right or left respectively. So the only way the partition doesn't move is if the pressure is the same on both sides. And then we're told we can assume that the specific heats for both the air and the carbon dioxide remain constant over the range of temperatures. So that will take to mean as being a perfect gas assumption. If we treat the carbon dioxide and air as ideal gases with constant specific heats, then that means that they're called perfect gases. And those specific heats are given here. Okay, so when I look at this, I think this is a first law analysis because we're given the initial state of the gases, and so we can find the initial internal energies of the gases, and then we're trying to find the final temperature of the gases. So that's related to internal energy, so that makes me think of the first law. So let's write out the first law for our system, and our system is going to be, it's going to contain both the carbon dioxide and the air. I'm going to choose the whole thing, just like that. And there's no heat transfer through this wall. There is heat transfer through the partition, but that's inside my system, so I don't have to worry about it. When we write the first law, let me go ahead and write it. When we write the first law like this, the Q into, which is the energy transfer into the system via heat transfer, that's through the boundary, through the dashed red line. And since this is a well-insulated tank, that Q into is going to be 0. Similarly, the work done by the system, this is the work done at the boundary. There is no, since the tank is rigid, there is no P to V work because the volume remains constant, and there are no paddles or rotating shafts, electrical work or springs or anything like that cross this boundary. So that term is also 0. Even though this piston in here can move, again, it's happening inside the system, so we don't worry about it. This W and this Q only are for what's happening across the boundary. So that one is also 0. Now the change in total energy of the system will be equal to the change in internal energy plus the change in kinetic energy plus the change in potential energy of the system. Now, if we assume that this is moving slowly, the piston's moving slowly, then and then we wait for everything to come into equilibrium, then the change in kinetic energy is going to be 0. It starts off with no velocity, no macroscopic velocity on either side, and then once it all settles down, there'll be no macroscopic velocity. So that change in kinetic energy is 0. Similarly, there's no change in potential energy because we have no change in elevation of within the system. So what this tells us in the end is that the change in internal energy of that whole system is equal to 0. Now the change in the change in the internal energy of the system, that's going to include the change in the carbon dioxide internal energy and the air internal energy. So we'll write that down. Since the system is comprised of air and carbon dioxide, I need to include both. So that's how I got that step. The partition, we're told, there's no energy storage in the partition itself, so we don't include that in our internal energy expression. Now, at this point, we need to write down what the change in internal energy looks like for both carbon dioxide and air, and what we're going to do is assume that they're ideal gases with constant specific heats. So assume the CO2 and air are ideal gases with constant specific heats. This is what we call a perfect gas. It's an ideal gas with a constant specific heat. And the reason we're assuming, so first of all, the assumption that they're ideal gases is a pretty good one. At this pressure and temperature, assuming that we have ideal gas behavior is a really good assumption. As far as assuming constant specific heats, well, we're told in the problem statement to assume that they're constant over the range of temperatures. And that would be a pretty good assumption if the temperatures don't change a whole lot. You know, if we're talking about temperature changes in each of these less than a few hundred Kelvin, then the constant specific heat assumption is a very reasonable one. Anyway, with those two assumptions, the change in the internal energy of the carbon dioxide will be the mass of the carbon dioxide times the specific heat at constant volume of the carbon dioxide times the change in temperature of the carbon dioxide. So it'll look like that. And then let me do the same thing for the air. That'll be the mass of the air times the specific heat at constant volume for the air times the change in temperature for the air. Okay, so again, the reason I can write the change in internal energy like this is because I'm assuming an ideal gas with constant specific heats. So one of the things I want to highlight is the final temperature I just wrote as TF in both cases because we know that when it's in equilibrium in the final state, the final temperature of the carbon dioxide and the final temperature of the air will both be the same, so I'll just call it TF. Okay, so now that we have this expression, we can rearrange it and solve for TF. We have everything we need to know in this equation except for the final temperature. We know the mass of the carbon dioxide that's given right up here is 3 kilograms. We know the mass of the air that's also given here is 1 kilogram. We have the specific heats at constant volume for the air and the carbon dioxide. Those are given right up here. And we have the initial temperatures of the air and carbon dioxide. They're given here. Okay, so let me go ahead and rewrite that equation so we can solve for the final temperature. Okay. If I did my algebra correctly, that should be the expression to find the final temperature of the air. And we can then substitute in and solve for the final temperature. And the final temperature comes out to be 426 Kelvin, or in degrees Celsius, it's 153 degrees Celsius. Okay, and it's what I did this calculation, I converted the temperatures over to Kelvin just because that's an easy way to do it. You're always going to be okay if you convert to an absolute temperature. So it's a good thing to do. Okay, and if you look at that temperature, 153 degrees C, you can see that's somewhere in between these two. And it's a pretty small change in temperature. You know, for the carbon dioxide, it's temperature difference of what is that now, like 24 degrees Celsius. It's about a 70-something degree Celsius change for the air, but that's still less than several hundred Kelvin. So this assumption of a constant specific heat is actually a pretty good assumption. Okay, so that gives us part A of what we're being asked to find. Now let's do part B. So to find part B, my thought process for that is to use the ideal gas law. So we know what the temperatures are both initially and at the final state. And I can find the initial volume because I know the pressure and temperature of the air and carbon dioxide initially. So I can find those initial volumes. And I know that the tank is rigid, so the overall volume should remain a constant. So that, you know, all those things add up to make me think of of using the ideal gas law. Okay, so let's write out the ideal gas law. So I know that the volume of the CO2 initially I can find, so that would just be from the ideal gas law, it will be the mass of the CO2, R of the CO2, that's the gas constant for the carbon dioxide, and then the initial temperature of the CO2, and that's all divided by the initial pressure of the CO2. So that gives me the initial volume for the CO2. I can do the same thing for the air. And then I know that adding those two together will be a constant because that tank is rigid. It's not changing its volume. So even though I know that the volume of the carbon dioxide and the volume of the air will change from the initial state to the final state, their sum should be the same. And so that'll be the same as the CO2 final plus the air final. Right? So I know that the total volume will stay the same. Okay. Now to find the final CO2 volume and final air volume, I can still use the ideal gas law. It's still the same mass, the same gas constant. Of course, the final temperature we just calculated, that'll be TF. And I know that the final pressure is going to be the same between them. Because in equilibrium, the pressures will be balanced. The partition's no longer moving from side to side. So the final pressures will be the same. So I'll just call it PF. So I'll just make a note over here. PF final, CO2 final will equal P air final, will just be P final. Okay, so I can combine these expressions. And so what I'm going to do is just rewrite this equation with these various terms substituted in. And then I will solve for the final pressure. Okay, so let's go ahead and do that. Just a lot to write down here. Okay. So there we go. Now if you look at that equation, we know everything in that equation except for the final pressure. Right? Everything else is given or we previously calculated it. And as far as the gas constants for carbon dioxide and air, we can calculate, let's see, are those given? They're not given, but we can easily calculate it. Just keep in mind that the gas constant is just Cp minus Cv. So we can calculate what that is or look it up in a table, but since they're given, the Cv and the Cp for each one, for each, the air and the carbon dioxide, we can go ahead and calculate what the gas constants are. So we can then rearrange this to solve for the final pressure. Let me go ahead and give you what that expression looks like. We won't go through all the algebra, but I'll just give you some final expressions here. So the final pressure I'm writing in terms of the tank volume and the final temperature, where the tank volume, the V total, is given here. A lot to write down. Okay, so there we go. So we can solve for the final pressure given these things, and if we throw in the numbers and do the calculation, what we'll get is the total volume. This is the volume of the tank. That comes out to be 1.46 cubic meters, and then the final pressure Comes out to be 250 kilopascals absolute. I'm assuming that the pressures that are given are absolute pressures, or that's it's actually about should be, yeah, this is about 250 kilopascals, so this is about 2.50 bar absolute. So that's what the final pressure is after doing the calculations. Oh, and I think I already, yeah, and the final temperature, of course, was given up here, 426. When you use the ideal gas law, you definitely have to use absolute pressures and absolute temperatures, so just remember that. And I think that covers everything we need to do for this problem. So this was a first law analysis problem. We recognize that there's no heat transfer through our system boundary because it's well insulated. We also realize there's no work across this boundary because it's a rigid tank. We wrote the change in internal energy of the whole system. It's comprised of carbon dioxide and air. We made use of the ideal gas relations and specifically for constant specific heats. So that's how we got to that expression. Did some rearranging, found the final temperature. And then to get the final pressure, we made use of the ideal gas law and the fact that the tank volume remains constant between the initial and final states because it's a rigid tank. And then from that, we could find what the final pressure is. Okay, we'll end the example there.